And now let us get back to that descriptive question which we were solving earlier. So we had solved the first three parts. Now we will focus on part D and part E. Now please read the question stem again if you want. It's the same question. Part D states, find the relationship between the force of friction and the angle of incline. Let's see how to answer this question. So there is an incline having the angle of inclination is theta. The wheel is rolling down the incline. We will start with drawing the forces acting on this wheel. So first force is mg acting downwards, then normal reaction which is acting perpendicular to the incline. And since the incline is rough, that means friction is going to act on the sphere in the upward direction. At this stage, by now, you should know that we need to break mg into two components. So the component of mg, which is perpendicular to the incline, that will be mg cos theta, and the other component along the incline will be mg sine theta. Remember the steps. F net is equal to ma is applied along the direction of acceleration. In this case, that will be along the incline, but perpendicular to the incline, forces needs to be balanced. So normal reaction should cancel out mg cos theta. So N is equal to mg cos theta. Please note, the friction acting on the wheel will be static only till the time the wheel is rolling without slipping. And according to the definition of static friction, it goes from a zero to a maximum value. And that maximum value is called limiting friction, whose formula is Fl is mu n, and n in this case was mg cos theta. And to answer the part D of the question, where we are supposed to find the relation between the force of friction and the angle of incline, we will write this. Friction is less than or equal to mu Sn, where mu Sn is the maximum value of the static friction which this incline can provide. And since n is mg cos theta, we will write F is less than or equal to mu s mg cos theta. So if we write only this much for part D, we are going to get full marks. But alternatively, we can say that from part B, we had figured out F is equal to ma and A is equal to g sine theta by 2. As you can see in all of this analysis which we had done earlier, for the part B, we had figured out A is g sine theta by 2. A stands for the linear acceleration of the hoop, and the value of friction was m into A. And that is what we have mentioned here. From the part B, F is equal to ma and A is g sine theta by 2. So if we put the expression of A in this formula, friction will come out as mg sine theta by 2. And that is why we can say for this specific question, the expression for friction is mg sine theta by 2. So as the value of theta keeps increasing, sine theta will increase and hence friction will also increase. Coming to part E of the same question, the angle of the incline theta is slowly increased from 0. Determine the angle in terms of coefficient of friction at which the hoop will begin to slip. So far in all the previous parts, we had assumed that the rolling was happening without slipping. This is the case when theta is big enough so that the hoop is beginning to slip. Now, since the hoop is beginning to slip, which means the friction acting on this hoop will be maximum, and that is called limiting friction. And now let us see how to solve this question. So let's start with the free body diagram of the hoop, where we have broken down the mg into two components, mg cos theta and mg sin theta. Normal reaction is equal to mg cos theta. In the previous part, part D of the question, we had derived friction is mg sin theta by 2. So read this. Till the time the hoop is rolling without slipping, friction acting on the hoop is static. And now if we focus on the angle of incline theta, if we keep increasing this angle theta, as theta keeps increasing, the value of friction will increase. And why is that happening? Because if you look at this expression, friction depends on sine theta. So friction is directly proportional to sine theta. When theta increases, sine theta will increase, and hence magnitude of friction will keep on increasing. But there is the limit to which the friction can increase, and that maximum value is called the limiting friction. The formula is Fl is mu times the normal reaction, where normal reaction was mg cos theta. So Fl is mu L mg cos theta. Now, in this critical scenario, when the friction has reached its maximum value, the angle of incline theta reaches a critical value. At that angle of inclination, the hoop will just begin to slip. So let's read, at this particular angle, the hoop is just about to slip, and the angle of inclination has been given a special name called the angle of repose. In order to find the angle of repose, we will equate the original expression of friction with the maximum value of static friction. In this situation, we are considering the angle to be alpha, so friction will be mg sine alpha by 2. And now let us equate F with Fl. So this is our equation, F is equal to Fl, the angle is alpha, so friction will be mg sine alpha by 2, which will be equal to this maximum value, mu L mg cos alpha. Let us try to make alpha as the subject. So what we'll do, we'll cancel out the mg on both sides. We'll take this 2 on the right hand side and cos alpha on the left hand side by cross multiplication. So we will get sine upon cos is equal to 2 mu l. Sine alpha upon cos alpha is tan alpha, which is equal to 2 mu l. And if we make alpha as the subject, we'll get tan inverse of 2 mu l. And this is the expression for the angle of repose, the angle of incline at which the hoop just begins to slip. And if you remember earlier, we had derived the angle of repose for a box kept on an inclined plane. Now let us summarize both the situations one by one. So we have two inclines. On one incline, let's say we have a box, and on the second incline, let's say there is a wheel which is rolling down. In both the situations, we are considering the angle of incline to be the angle of repose. So in case one, when we are dealing with the box, at this angle, the object is just about to move, whereas for the hoop, at this angle, the hoop is just about to slip. And in both these cases, the friction acting will be maximum. It is limiting friction. So maximum value of friction will be applied and the direction will be up the incline. Earlier, we had derived the angle of repose for the box on an inclined plane case. The alpha was tan inverse mu s. And for the wheel case, we just derived alpha was tan inverse of 2 times mu s. But I would recommend not to remember this formula because this expression is valid only under a certain assumption. This expression is valid if the object is either a ring or a hollow cylinder. And why is that? Because the moment of inertia is mr square. If you analyze all the steps, how did we get to this expression? We had used the expression of I is equal to mr square. And even if we go back to the main question stem, look at the statement 1. Moment of inertia for the hoop is mentioned to be mr square. And if you recall the part B, when we solved the question, we used torque net is equal to I alpha. And instead of I, we had used mr square. And since we had used I as mr square in the analysis, eventually we get this expression tan inverse of 2 times mu s. That is why I told you not to remember this formula because this is valid only for a ring and a hollow cylinder. Imagine there is a disc or a solid cylinder or a hollow sphere or a solid sphere where the moment of inertia is not mr square. In those cases, the angle of repose will of course be different. But for the box which is kept on an inclined plane, alpha is tan inverse mu s. This expression we can remember because this we can directly use in the exam questions.